Okay, well, thank you, Christine. And thank you for giving me the opportunity to present you my work, our work. But before starting, I would like just to announce a conference we are organizing next year in Madrid. It's also nonlinear dynamics, mathematics and physics. So if you want to just come and spend some time with us, we'll be happy to host you here. In principle, we were organizing it for this year, but due to the problems, we were not as brave as you to do it online. So we've just decided to postpone it. Okay, so this is the outline of my talk. I will give you a very brief introduction on the topic. I will just say a few words on the kind of systems that we study, the methodology, results, and I'll sum up with the conclusions. The thing that I will show you, I will present you is appeared in this paper, right? And the key point is the thing you can see here, Lagrangian descriptors, that maybe I think most of you might not have heard about them, but they are a very simple tool to study chaotic systems, and it is extremely efficient and again, very, very simple. There's a myriad of different tools to study chaos. I mean, Poincare surface of section and Lyapunov exponents are the most, let's say, famous ones. But there's also frequency analysis, SALI, fast Lyapunov indicators, orthogonal version of it, MECNO, and and many, many more. And maybe not all of them, but many of them have something. I mean, the same thing in common, right? You want to study some reference trajectory. You want to see whether it is a stable or unstable. If it is unstable, how much is it, and so on. And typically you just take one or two neighboring trajectories and you study what's going on around it. You can do it this way, or you might linearize a motion, but the idea is the same. So fast Lyapunov indicators, for example, you just take an initial distance, a separation, and you see whether it becomes larger or it keeps more or less constant. In SALI, you take two initial vectors, and if this angle tends to 0 or pi, that means that the reference trajectory is unstable or chaotic, and if it remains more or less constant, you have an unstable periodic orbit or a stable orbit, or in general. Okay. So the interesting thing of Lagrangian descriptors is that you do not have to do that. You just have to run your trajectories, and that's it, right? And all information somehow is encoded in the trajectories themselves. So it's like dynamics for dummies. I mean, you do not have to know anything about chaos, nonlinear dynamics, or so on. I mean, if you know how to solve the equations of motion, you can use this tool. Okay, so the system is we study molecules, and the first question is, why do we study them? And well, because they are excellent platforms to use dynamical systems theory tools to analyze them, right? They are in general extremely harmonic, and some of them, like the ones that we study, are very simple because they do not have so many atoms, so you don't have as many degrees of freedom as in very large molecules, right? So the one that I will present to you is formed by these three atoms: lithium, carbon, and nitrogen. Carbon and nitrogen have a triple bond, so their distance keeps more or less constant. And then only lithium moves around them, right? It can have this scratch motion, so kind of vibration, or it can rotate around it, right? Okay, so we have three atoms. 3 atoms means 9 degrees of freedom, but you can just assume that you have no rotation, and then you just have three different coordinates to define the configuration of your molecule. The first one will be this r, the distance between lithium and the center of mass of the dimer. The second one will be this angle, and the third one will be the distance between carbon and nitrogen, which we will assume that it is constant, right? Which is a reasonable approximation. Okay, so we just have r in theta in principle. That means we have 2 degrees of freedom. So the Hamiltonian, in principle, if you use these kind of coordinates, which are the Jacobi coordinates, looks like this. But again, if we assume that the distance between carbon and nitrogen is constant, then, well, here the mu's are reduced masses, But if we take this R, assume that R is constant, then the kinetic energy term, PR small r is 0, and then the Hamiltonian just look like that. Okay, so we have kinetic energy term for the big R, kinetic energy term as a function of theta, and then the potential energy. Okay, the potential energy looks like this. We have two minima, which correspond to those collinear configurations of the molecule, those isomers, and we say that we have a reaction every time lithium crosses from one side to the other side, right? And for that purpose, it has to overcome that saddle point that appears in red, that sits over the minimum energy path that connects both minima. Okay, and then we also have another potential energy term that accounts for the carbon and nitrogen, but I will simply skip it. Okay, what are the Lagrangian descriptors? Originally, they were developed to, or they have extensively studied to study oceanic flows, right? So there you've got a plot, and you can see very nice, I mean, a very clear pattern, right? And those lines that are shown correspond to the invariant manifolds that determine the dynamics in the system. And it is, I mean, the first definition was simply that, right? You have your equations of your flags, and you just have to take the norm of them, and you know, you take the square of them, the square root, and you integrate it over time, forward and backwards in time. And this is just an example, very simple one. If you apply to Duffin equation, you can see that when you change that integration time, you start to see some structure, right? And that structure is again are the invariant manifolds that form the homoclinic or deuteroclinic tangle in the system. So it is something simple, but it does work. Okay, that definition was later on improved using P norms, and then you just have to, well, take the absolute value of the terms of your flags, integrate them forward and backward in time, and that is the Lagrangian descriptor. And then what you see is, I mean, this is another example for a saddle point. If you calculate it in that range and you take a section over it, you can really see that there's a singularity at some point at the origin, and that corresponds precisely to one of the manifolds of the system, right? So that is the way they work, right? Every time you have an invariant manifold, there's a singularity in the Lagrangian, and that is the way you can identify them. Okay, we have applied it to our molecule. I mean, actually, we have applied it to a few more of them. And I will just talk about the first two situations, just the results that we have for 2 degrees of freedom. Then a very interesting saddle node bifurcation, which is also important from the chemical point of view. And I will just show you one result for the situation with 3 degrees of freedom, if I have enough time. Okay, so this is, I mean, typically, you know, I mean, if you take a Poincare surface section for the system along the minimum energy path, that is the angle. So it's like the angle that lithium forms with the CN direction, right? And that is well, a transformed momentum. And you can see that when the energy is small, then all the phase space is filled by invariant array, right? Or chains of islands. That means you have regular motion. If you increase the energy, then you start to see chaotic motion, right? And you also see that then the lithium atom could also see it on the other side, right? Because, you know, the minimum, I mean, you have an energy that is slightly larger than the energy of the well minimum. So you can also localize the atom there, but then in that region, the motion is almost completely regular. If you increase the energy further up to that value, 3,500 centimeters minus 1, you can see that then the lithium atom can move from one isomer, I mean, from one well to the other well, and then we say that we have a chemical reaction, right? Now, if you compute the Lagrangian descriptors for in that region of phase space, what you get is something like this, right? So you've got a picture that is like the dual, it provides a dual information from Poincare surface of section. So Poincare surface of section works well for the regular part, right? But here, Lagrangian descriptors, I mean, you can see something here, the chain of islands here can also see, but you know, it is almost constant. The interesting thing is that it provides information on the chaotic part. So here with the Poincare surface of section, you see nothing, but here you can really identify some lines, and those lines correspond to the invariant manifolds. Okay, you can also superimpose it, and you can see that this tool really works. If you increase the energy, again, you have the same situation, so you can really see that with the Poincare surface of section, just there's a chaotic sea of points, but nothing else. But here you can really see a very clear structure. Okay, and you can also visualize here a region that is very interesting. It corresponds to a stability island, right? That is also visible in the Poincare surface of section, right? Here, there's something going on, right? I mean, the chaotic trajectory cannot enter there. And I will talk about it in a couple of minutes. But then again, if we increase the energy further, you see exactly the same thing, right? The accessible region of phase space becomes larger, but you know, motion becomes more and more chaotic. And again, Lagrangian descriptors are able to identify the invariant manifolds in that region. Okay, so let's go back to that stability island that was there. I mean, the origin comes from a subtle node bifurcation, right? So at a certain point of energy, I think around 3,300 centimeters minus one, there's a bifurcation, and this periodic orbit that is marginally stable appears out of the blue, right? And when you increase the energy, it bifurcates, right? So it disappears, and then you've got a stable periodic orbit on the left, and then an unstable periodic orbit on the right. Okay, the origin of this kind of bifurcation is, as you might know, that you've got some manifolds that become tangent, right? And with the Lagrangian descriptors, you can really see the situation very clearly, right? So this is a plot below the bifurcation energy. You can see here some lines. Those lines are the invariant manifolds, right? That come from some other trajectories in phase space. When you increase the energy, these manifolds start to be closer, and then, I mean, almost tangent. And when the bifurcation takes place, they become tangent. Then here appears a parabolic point, and that is where this marginal stable periodic orbit appears. If you increase the energy further, you can really see this structure that I just mentioned, right? So this is the stability island, and well, here in the middle somewhere should be the stable periodic orbit, and here at some point is the unstable one. If we increase the energy a little bit more, we've got the same picture. This is again the stability island that has moved leftwards, while the unstable periodic orbit has moved rightwards. And we can compute the manifolds using all the tools, and this is the exact calculation. In blue, you've got the stable manifold, in red, the unstable manifold. This purple triangle corresponds to the point where the unstable periodic orbit is localized, and you can really see that there's an excellent agreement between Lagrangian descriptors and the calculations that you use using all the standard tools, right? So again, the interesting thing is that, you know, we can get this picture by just solving the equations of motion, right? That is the interesting thing. We do not have to linearize motion or use some other more advanced tools to identify the manifolds of the system. Okay, and I think I've been quite quickly. Well, just I will just show you what happens when we have 3 degrees of freedom. And in that case, what we do is just assume that this distance between carbon and nitrogen is not constant, but they can move, right? The thing is that, I mean, as I said at the beginning, this bound is triple. So the motion has, I mean, is very completely different from the one that we can see here, right? I mean, the vibrations take place at much larger frequencies. Okay, so the Hamiltonian is the one I showed you at the beginning. So we can also do the same thing, right? We just take some initial conditions, we propagate them, and we compute the Lagrangian descriptors for that case. And we make the similar plots from the one that I've shown you. And the interesting thing is that we take the initial conditions by changing the kinetic energy in this third degree of freedom, right? So we vary it and we see what happens. And what happens is that we have a very similar situation from the one that we had observed for 2 degrees of freedom, right? So at the beginning, we include no kinetic energy. We have that this initial energy goes all to the r and theta degrees of freedom. So we have a very similar plot from the one I showed you at the beginning. Again, the motion is 3D because we have this term here that couples all the 3 degrees of freedom and also the potential energy. But this coupling for r, it's not so important. Then we increase the kinetic energy in that degree of freedom. Then the energy that we have accessible in the Poincare surface of section is smaller. So somehow it looks like if this plot doesn't look like the one with 3,500 centimeters minus one energy, but just 2,000 centimeters minus one, right? So it becomes smaller and the motion is also more regular. And if we increase the energy, but if you increase it further, then you have the same situation, right? So the accessible energy is smaller and then the motion is more and more regular. So the more kinetic energy you add to the small r, the more regular the motion is. So with this, I think I've been quite fast. I just come to the conclusions and the take-home message, which is essentially that Lagrangian descriptors allow the identification of invariant manifolds in molecular systems. And with this, I'm done. So if you have any questions, I will be very happy to answer them. Thank you.
Okay, so thank you very much. Just to remind you, because plenty of attendees showed up after the introduction, you are encouraged to type in your questions into the question and answer box. And since Fabio has finished quite early, there's still some time for you to collect your thoughts. So I am still waiting for the question and answers in the box. I will read them out as they come. In the meantime, maybe I start with a question if you don't mind, Fabio. You're still around? Mm-hmm. So you initially said, so this tool can be computed from a single trajectory, but then you showed your plots. Mm-hmm. They looked like this was computed for a whole collection of trajectories.
Yeah.
So it's not quite clear to me.
Yeah. What I mean is that you do not have to study the neighborhood of the trajectory, which is what you usually have to do, right? So I don't know, for example, if you calculate the fast Lyapunov indicator, you have to see to linearize the motion and see what happens around it, or you compute how the distance changes between your reference trajectory and another one that is close to it. It is true. You have to do it many times for many trajectories. But the interesting thing is that for each of them, you do not have to do any. You do not have to study what's going around it. That's what I meant.
So you do not need any computation of variation.
Exactly. That's what I meant. So somehow, true, you have to solve it for not only for a single one, but for many of them, to see the differences. So and then identify the manifolds. But somehow all the information is encoded in the different trajectories, right? Because the important thing is that the manifolds have a different motion from the rest of the from the chaotic trajectories that are found in phase space, and then that is important thing. So if you have an initial condition that sits on one of the manifolds, then you can really identify it. You have many, so you can really see this continuous line.
I see. So any more questions from the others?
May I ask a question?
Good, go ahead.
I want to ask, is it really correct to apply classical mechanics to like the motion of the molecules?
I don't say it again.
You apply classical mechanics, not quantum mechanics, to
Yeah.
the motion of the molecules.
Yeah.
How correct is that?
Yeah, I mean, it depends on what you want to do. That is true. I mean, sometimes you cannot do it, but if you have atoms that are, let's say, I mean, not too small. So, I mean, to study the motion of nuclei, that works well. Another question is what happens with the electrons, for example, because then, I mean, this makes no sense if you want to describe the motion of the electrons. In that case, you really need to go into the quantum regime and use quantum mechanics. Yeah.
Okay, thanks.
Any further questions? If not, I may have another one. So you have this parameter tau, and you presented everything in dimensionalized units. So it wasn't quite clear to me. Is that tau? Is it very large compared to the typical trajectory lengths you compute, or like how does the whole thing depend on the tau?
No, it is just like 10 times. If you have a look at the periodic orbits of your system. So in our case, it is like 10 times larger. So that's enough. Yeah. So it is not large. I mean, if you look at the numbers, they are of order 10 to 4, but still that is not much in this kind of system.
Okay. So excellent. So there was no other